Module 4.4, Standing Waves in a Tube Closed at Both Ends. Last time we were looking at a tube open at both ends. We had nodes at both ends because we noticed that the pressure, the spacing between the molecules, does not change. And when we don't have a change, that's where we have a node, no change in pressure. Let's see now what happens when we close both sides of the tube. Now, as we look at the tube, we see that the pressure gets less, and then as the vibration goes the other direction, the pressure increases greatly. So this would show us that we've got a great pressure change on the ends, and in the middle, the spacing between the molecules remains relatively constant, so there's no change. So the nodes and the antinodes are the opposite of what we have in a tube that's open at both ends. So our new rule is with a tube that is closed, there is an antinode at the closed end always. And just like an open tube, as we get more harmonics, we get more nodes and antinodes. So if we have an antinode there, we'll have a node in the middle. And again, it turns out this is half of a waveform. So we have this part here and this part here. So as it turns out, the formula for a tube closed at both ends is the same as a tube open at both ends, which is F equals V over 2 times L. And if we want any harmonic on it, then we add the harmonic number. Now, two things here. First of all, we had to have end correction for a tube open at both ends. When it's closed at both ends, we don't have the air at both ends, and then we don't have to use end correction. So this ends up being the formula that we can use for a tube closed at both ends. To review, closed ends of a tube are always pressure antinodes. The frequency of any harmonic is NV over 2L, where N is the harmonic number, V is the speed of sound in air, and L is the length of the tube. No end correction is needed for a tube closed at both ends. The wavelength of any harmonic is 2L over N, and the frequency of any harmonic is N times the fundamental frequency.